Good morning to all. Today we'll discuss about the second part of the dams chapter of theory of structures subject. So before going into the lecture, once we will revise our previous class topics. So in the previous class, you have learnt about definition of a dam and what are its main purposes and various forces acting on a dam we have seen, that is self weight, horizontal water pressure, and because of these two, a resultant force R. Also, we have calculated the distances at which these three forces are acting, and we have derived the equation for the calculation of these forces in the previous class. So today our main objectives are, after completion of this class, you would be able to calculate the value of Z. As I have mentioned in the previous class, R cuts the bottom of the dam at a certain distance from vertical face of the dam. So that we have mentioned it as Z. So we'll derive an equation for Z, and also we'll calculate the eccentricity, and later we'll derive the equations for various stresses at the bottom of the dam. So these are the main objectives of this class. So let's look into the topic. So the calculation of Z, it requires writing an equation, moment equation. There is nothing but by using principle of moments, we can write a moment equation about heel, that is point A. So taking moments of all forces about heel, that is A, we have sigma ma equals to 0. So what are all forces are acting about A? First one is P. P is at a distance of h by 3 from A. So force into perpendicular distance. So force P into perpendicular distance is h by 3. We get moment. So this is a clockwise moment with respect to point A. And in the same manner, we can write the equation for W. So W equals to W into X plus W into X. This is the distance X equals to R into this distance Z. So these are the moments here. So here, for resolving R at the base, horizontal component P, its line of action of passes through the heel, So moment is equals to at base. I'm saying at base. If we consider at base, there is nothing but P will be acting like this. So there won't be any particular perpendicular distance. So because of that P, there won't be any moment. So P into 0, 0. And vertical component of W, we can write it as W into Z. So if we simply shift our W from here to here, so that is this. So W into Z equals to R into Z. So because of this relation, we can write R in terms of W. R in terms of W. So to substitute R value here, we have taken this condition. Therefore, R into Z equals to W into Z, and ultimately we will substitute that RZ here W Z. So P into H by 3 plus W into X equals to W into Z. So hence we get an equation for Z as P into H by 3 by 3 into W plus X. This can be written as like this. Like this. So this is the Z equation. So calculation of eccentricity here, after calculation of Z value, we need to calculate the eccentricity value. So if the resultant passes through the center of the base, the eccentricity is 0. So this point you need to remember. So if this R, if it passes through the center, that is nothing but from B by 2. It is B by 2 here and B by 2 here. If R passes through this center like this, so E will be 0. But it is not here, it is not passing through the center. It is passing through a certain distance called Z. So hence we can write it as P by 2 plus E equals to Z, or simply E we can write it as Z minus B by 2. The same here, right? So or else we can write EF, that is nothing but E, is equals to dE minus dF, which is equals to Z minus B by 2. So this is the eccentricity value which we need to calculate and check whether if E is equals to 0, this condition, there won't be any, I mean to say, there won't be any turning effect on the dam. I mean to say overturning effect, right? So this E plays a major role in the design of a dam, because if E is as much as lesser value, it is directly implies the stability of the dam. It means if E is less, stability of dam is more, right? Next is stresses at the bottom of dam. So calculation of the direct stress. First, this will be the first stress. Direct stress will be because of due to self weight, that is force is equal to W, and area on which it is acting is B into 1. Why it is 1? Because I have mentioned in the previous class in note that we'll consider for unit length of dam, right? That is what 1. So stress is equals to mathematically force by area, and force is W here, and area is B into 1. So this direct stress will be like this. I mean to say the force, and this will have this stress will have a nature of compressive in nature. So this direct stress will have compressive nature, and it will be having a pressure distribution diagram of uniformity. That means it will have a rectangular shape of pressure distribution diagram, right? So this we can write it as P suffix T, which is shown here. Next is calculation of bending stress. So from the theory of simple bending, M by I equals to sigma by Y, and sigma is the bending stress, M is the I is the moment of inertia, and Y is the distance from the extreme fiber to the centroid. So if we consider the bottom portion of the dam like this in this figure, we consider unit length, and we have width as D in the bottom. So moment W, for moment W is acting at a distance of E, right? So that is the eccentricity, this W, and moment is W into force into perpendicular distance, which is E, and I will be like this, not BD cube by 12, it will be DB cube by 12, right? So D is 1 and B cube by 12, and Y will be our B by 2. So after substitution of these values, we'll get as, once we'll try to solve this. ఎక్కడ ఉన్నారు ఇప్పుడు? కామాక్షి వీళ్ళు కామాక్షిపురం అడిగారు. పోచమ్మ టెంపుల్ తెలుసా? అక్కడ నుంచి సెకండ్ రైట్ అండి. పోచమ్మ టెంపుల్ ఆనుకోని ఒక రైట్ ఉంది. ఆ రైట్ కాకుండా సెకండ్ రైట్ లో లాస్ట్ లెఫ్ట్ సైడ్. ఓకే. So if we solve this equation, 1 by I into y ms w into e by I is b by 12 into b by 2. So here we have 6e by b square, right? So ultimately we'll get a value of 6we by b square. So for compression we'll give a value of plus, and for tension we'll give a value of minus. So what will be the bending stresses in case of compression and tension? Plus or minus 6we by b square. So if we draw that particular bending stress distribution diagram, on the toe side we'll be having compression, on the heel side we'll be having tension, because of water pressure P, the dam may try to overturn just like this. It is just an imaginary thing. Actually it doesn't happen like this, but so it may have a effect like this because of horizontal pressures and various other forces, wind pressure and etc., wave pressures. So because of such pressures, the dam may try to overturn like this side. So as we can see, there will be a pressure here on the toe side. So because of that pressure, it will be of this soil will be under compression, right? While this particular material, whatever which is there here, this particular material will be under tension, right? This is tension and this is compression. So on the toe side compression, and on the heel side it will be a tension. So as we draw the stress distribution diagram, on toe side it will be positive, on the heel side it will be negative. As the magnitudes are both same, the triangles will be similar but on the opposite sides. So this is minus sigma b and this is plus sigma b. So bending compression is plus 6we by b square, and bending tension minus 6we by b square. The stress results in the tension at the heel and the compression at the toe. So this is what I have mentioned. This is an important point for objective point of view for any competitive exams. This is a note. So with this, we have calculated different stresses direct stress and bending stress. As these two stresses are developing in the dam material itself, we'll be having a combined effect of these two stresses. That we will see now. So sum of direct stress and bending stress, this is the direct stress diagram, and this is bending stress diagram. Right? Total stress at the toe of the dam and heel of the dam we need to calculate now. So in direct stress diagram, as the pressure distribution diagram is rectangle in shape, on toe side and heel side we are having same value PD. That is PD, what we have, PD value W into B into 1, right? So first we'll calculate the total stress at toe side and then heel side. So total stress at the toe of the dam, P max equals to PD plus sigma B. PD plus sigma B. The combined effect, right? So PD is W by B and sigma B is 6WE by B square. Upon, so if we calculate, if we take W by B as common, we'll get a value of W by B into 1 minus 6E by B, right? So this will be the maximum pressure. So it is the maximum stress, I mean to say, in the dam, which is located at toe point. In the same way, if we calculate the total stress at the heel point, as PD is same value and sigma B here will be having as minus value because it is under tension. So PD minus sigma B, which is equals to WB by W by B minus 6WE by B square. So if we take common W by B again, W by B into 1 minus 6E by B, and this particular stress is minimum. So with this we can say that in a dam structure, in the bottom face of the dam we'll be having two different stresses. One is at the toe and one is at the heel. While at the toe we'll be having maximum stress, and we can say it as maximum compressive stress, and at the toe, at the heel, we'll be having minimum stress because it is subjected to a bit tension. So we can see ultimately we'll get the both P max and P minimum will be having positive values itself, right? And if you draw the final stresses distribution diagram, as Pmax is on the toe side, we'll be having some higher value here, and the minimum values on the heel side will be having a lower value on the heel side. And if we join these two by a linear, by a line, we'll get a shape of trapezoid, right? So this will be the shape of a final stress distribution diagram of a dam, which is subjected to various stresses, most commonly direct stress and bending stress. So this is what we are intending to learn in this particular tutorial. So these values, I mean to say these equations, you need to remember for your numericals, so that it will be easier for you to just substitute the values what all he has given in these equations, and ultimately you can get the required answers. So for calculating of stresses at the bottom of the dam, you have calculated initially direct stress, and second one is bending stress.